Assalamualaikum warahmatullahi wabarakatuh. Today we are going to discuss about assignment Thermodynamic 2. My name is NABIHAH binti ROSIDI. My metric number is 202458.
Hello, my name is Uzair bin Shukri and my matrix number is 202457.
Hello, my name is SYAZWIE by AREFF. My matrix number is 201736.
So we are going to continue about our question. So this is our question. We decided to choose to design a power cycle for internal combustion engine that is suitable to produce network output in range of 500 to 600 kilojoule per kilogram. So we need to calculate the backward ratio, BWR, the efficiency, the temperature, and pressure for each point in the cycle using both assumption, which is cold air standard assumption and also air standard assumption. At the end, we need to compare the result and discuss. So we also need to include our drawing of PV and TS diagram of the cycle. Okay, so this is we choose to do auto cycle. So this is the PV and TS diagram of auto cycle. At first, we assume that K is equal to 1.4, which is cold air standard assumption. Then we assume 0.1, which is T1 is equal to 300, P1 is equal to 100 kilopascal, and R is equal to 9, Q in is 100 kilojoule per per kilogram. So like I said, we need to find T and P for all points, the efficiency and the backward ratio. So first, we can use the process 1 to 2, which is isentropic. We can find the value of T2 by doing T2 over T1 is equal V1 over V2 to the power of K minus 1. We know that V1 over V2 is equal to R. Then we can substitute the V1 over V2 with R. So we can fill in the value that we know, which is T1. Which is T2 is equal to 300 times 9 to the power of 1.4 minus 1. Then we get the value of T2, which is 722.47 Kelvin. Then with the same process, we can find the pressure for pressure 2, which is P2 over P1 is equal to V1 over V2 to the power of K. Like we also know that V1 over 2 is equal to R. Then we can substitute it with R. So P2 is equal to 100 times 9 to the power of 1.4, which is P2 is equal to 2167.40 kilopascal. Then from table A2, when K is equal to 1.4, CV is equal to 0.718 kilojoule per kilogram. Then we can get the value of T3 by using equation Q in is equal to CV T3 minus T2. We use this equation because it is at constant volume. So we fill in the known value, then we can get the T3, which is 2115.23 Kelvin. So we continue with process 2-3, which is constant value, to get the value of P3. So we can use equation P2 V2 over T2 is equal to P3 V3 over T3. We know that V2 and V3 is constant volume, so we can cancel it out. And P3, and then it becomes P3 is equal to P2 T3 times T3 over T2. So we can fill in the the value, and we can get the value of P3, which is 6345.66 kilopascal. Then we continue with process 3 to 4, which is isentropic. T4 over T3 is equal to V3 over V4 to the power of K minus 1. So we know that V4 over V3 is equal to R. Then we can use that in V3 over V4, but we need to do that T4 is equal to T3 times 1 over R to the power of K minus 1. So we fill in the known value, then we get the T4, which is 878.34 Kelvin. Then we proceed to find the pressure for point 4, which is P4 over P3 is equal V3 over V4 to the power of K. Then we know that V4 over V3 is R. So P4 is equal to P3 times 1 over R to the power of K. Then we substitute the known value and we get the value of P4, which is 292.77 kilopascal. Then we can find the value of Q out to use it to find W net. Okay, so Q out is equal to CV T4 minus T1. Then we fill in the value. Then we get Q out is equal to 415.25 kilojoule per kilogram. Then we can find the W net since we already assume the value of Q in and we already find the value of Q out. So W net is equal to Q net. Then W net is equal to Q in minus Q out. So we get 584.75 kilojoule per kilogram. Then from that we can get the efficiency of the cycle, which is W net over Q in. So we get efficiency is 58.48%. We also can find the backward ratio of the cycle by using the equation PWR is equal to W compression over W expand. So it's equal to U12 per negative U324. Then then it is equal to CV times T2 minus T1 over CV T3 minus T4. Then we can cancel the CV because it is the same. We get T2 minus T1 over T3 over T4. Then we fill in the value. We get the BWR is equal to 34.16%. So I'm going to pass it to AKRAM to continue with extended assumption.
So we're gonna continue our calculation with extended assumption. So this is our graph for PV and TS. So extended assumption. So we not assume that K equals to 1.4.
Yeah, I'm sorry. Actually, it is K is equal not equal to 1.4.
Yeah,
sorry.
K equals to 1.4. So we assume the value for our calculation. So equal to T1 equals to 300 Kelvin. P1 equals to 100 kilopascal. Ratio equals to 9 and Q in equals to 1000 kilojoule per kilogram. So we will need to calculate the temperature and pressure for all points. Second, we need to calculate the efficiency. And lastly, we need to calculate the backward ratio. So next. So we know that R equals to 9. So it is equal to V1 over V2 and equals to V4 over V3. So we know that CV of air is equals to 0.718 kilojoule per kilopascal times Kelvin. So for find the temperature for temperature or pressure for process one into two is isotropic. So we know that from table A17, VR1 equals to 6 to 1.2 and U1 equals to 214.007 kilojoule per kilogram. So we need to calculate. We know that VR1 is 6.6 to 1.2. So we're gonna calculate the VR2. So we get the VR2 equals to 69.02. Next. So to calculate temperature for point 2, so we're gonna do a interpolation. So we have the value from the VR2. So VR2 is between the 69.7 and 67.07. So the temperature for that is from 700 Kelvin to 710 Kelvin. So we're gonna do a interpolation for temperature. So we get T2 equals to 702.75 Kelvin. So we also need to find the U2. So the U2 we get from the table above. So we calculate and we get U2 equals to 514.5 kilojoule per kilogram. Next, we gonna use the formula P2 equals P2 V2 per T2 equals to P1 V1 equals per T1. So from this equation, we gonna find the P2 and we take the value from above and we get the P2 equals to 2108.25 kilopascal. So next. So for the process 2-3 and custom volume. So we gonna do we know that Q in equals to U3 minus U2. So we get the Q in, we assume the Q in is 100 kilojoule per kilopascal. So and we get the value for U2 is 514.15. So we can calculate the U3. The U3 is equal to 1540.15 kilojoule per kilogram. So to calculate T3 for the process 2 to 3, so we gonna use the interpolation also. So we get the U from above and we wanna see the table from table A17. So we get U3 is between 1487.2 and 155 1534.9. So we from that value we calculate the temperature and we temperature 3 and we get temperature 3 equal to 1828.25 Kelvin. So next we need to find VR3 also. So we just key in the value into this formula and we get 3.77. So next. So this is another thing to find the P3. So we know that P3 V3 over T3 equals to P2 V2 over per T2. And so we know that V2 and V3 has a same volume. So we can cancel out the V. So we just have a P3 equals to P2 times T3 over T2. So we use the value from above and we get P3 equals to 5484.75 kilopascal. So for the net process is process 3 to 4 is equal to isentropic. So we know that R equals to 9. So VR4 over VR3 equals to 9. So we gonna move a VR3 to the right, and we get VR4 equals to 33.93. So next. So from we get VR4, so we must calculate the temperature and U4. Why we need to calculate U4? So because we're gonna use in WordNet, which is Q out, the formula of Q out. So we get the temperature of 0.4 equals to 903.57 Kelvin. And so for U4, we get 677.56 kilojoule per kilogram. So the another formula is we know that V4 over T4 equals to P1 V1 over T1. So V1 is equal to V4 because have a same volume. So we cancel out the V and we get the formula P4 equals to P1 T4 over T1. So we calculate the P4 and we get the 300. The value is 301.19 kilopascal. Next. Okay. So from the above, we get U1 and U4. U1 you get from the table, and U4 from the calculation. So we just put the value into the formula, and we get the Q out equals to 463.49 kilojoule per kilopascal. And we assume the Q in equals to 1000, and we just put in the Q out value from the above, and we get W net equals to 536.51. So we get the W net. After that, we must calculate the efficiency of this assumption. So the formula is efficiency equals to the W net over Q in. So 536.51 over 1000, so we get 53.65%. So for efficiency. So for payload ratio also, we need to calculate. So the formula for the payload ratio is W compression over W expansion equals to CV T2 minus T1 over CV TT minus T4. So CV we must cancel out. So we get the formula T1 minus T2 minus T1 over T3 minus T4. So we key in the value into the WR, and we get the WR for this standard air assumption is 43.56%. That's all from me. I give to the Uzair to give the presentation.
Next slide. Okay, thank you, Akram. So this discussion of this assignment. So we chose autocycle for this assignment. And autocycle is an analyzed thermodynamic cycle that describes the functioning of a typical spark ignition piston engine. So it is the most common thermodynamic cycle found in automotive engine. The autocycle is a set of processes used by spark ignition internal combustion engine. This engine will engage a mixture of fuel and air, compress it, cause it to react, and then expand the combustion product. And the last one is it will reject the combustion product and replace them with a new charge of fuel and air. So in this assignment, some assumptions need to be made in the calculation process. That is, we assume T1 is equal to 300 Kelvin, P1 equal to 100 kilopascal, ratio equal to 9, and Qin equal to 1000 kilojoule per kilogram. So as you can see in the table, we can see that although the initial value is the same, but the final value for both the call as standard and as standard assumption is different, especially in the QR, WNet, efficiency, and BWR, because the call as standard has k equal to 1.4, while as standard for k is not equal to 1.4. So according to table 1, most of the value for call as standard is a little bit higher than the as standard assumption. Since the actual gas power cycle are very complex, so as standard assumption are used to minimize the analysis to even is to a manageable level without greatly divide the use of it. So to make the analysis even easier, call as standard assumption are used. So the working fluid in as standard assumption is air that behave like an ideal gas, and all of the process in the cycle are internally reversible. While for the call as standard assumption include the fact that A can be treated like an ideal gas at the room temperature with constant specific heat. So that means the differences of the call as standard and as standard is the call as standard we need to assume that it has constant specific heat at room temperature. So the WNet in call as standard assumption is 1584.75 kilojoule per kilogram, while for the air standard assumption is 536.51 kilojoule per kilogram. That means the objective of the assignment was achieved, which is the WNet should be in the range of 500 kilojoule per kilogram to 600 kilojoule per kilogram. Called as standard assumption has higher efficiency value compared to air standard assumption. That is 58.48% for cold as standard, while for air standard assumption is 53.65. Even though the cold as standard has higher efficiency value, but air standard assumption is more precise because the value is the nearest to the actual cycle. The cold as standard has higher efficiency value just because the Q the QE is little, the WNet is higher, so that's will make the efficiency higher. So that's all from us. Thank you.
Thank you.